Alright, so in this video what we're going to do is talk a little bit about normal Bernoulli and how it impacts lift generation. So Bernoulli's normal equation is a little different than the equation used for streamlined Bernoulli. And the concept is actually pretty straightforward and simple. So let's actually go back to a problem that you probably once saw before. This idea of taking a bucket and putting a bucket on a string and swinging that bucket in a circle around you. And what you can imagine happens in this particular scenario is that anything inside of the bucket is actually going to get stuck to the bottom of the bucket. And the reason that we know this is that we understand that circular motion, in this case, or motion in a circular path, is going to cause an acceleration that's going to shift the contents of the bucket to press against the bottom of the bucket all the way through that circle. So the idea of the normal Bernoulli equation is actually pretty similar. So what we take a look at for the normal Bernoulli equation is an analog to this bucket problem. So we're going to say, imagine you've got a streamline like this, and that's going to be the path of this little chunk of fluid. You can even think of it as a bucket of fluid, right? And that chunk of fluid, as it goes along that path, is going to have to be acted upon in order for it to go around that curve. So for the bucket problem, you know that you're going to have to pull towards you with a certain amount of force bucket, in order for you to keep that bucket going in a circle. On this problem here, you know that in order for this particle not to just keep going straight like this, but for it to curve downwards, you would have to actually apply some amount of force on that particle, so F. And what's cool is that the two equations, or the two systems of equations, are actually pretty similar, right? So what I'm going to say here is this force is actually related to the delta pressure in the normal direction. So delta pressure over the delta normal direction. And in this case, this is the normal direction to the streamline N, like this. And what we can also see is that in order for this to go through this curve, you would actually have to have a greater pressure acting on the outside and a smaller pressure acting on the inside. So this would be my pressure difference that essentially is pushing this particle through this path. And then what I'm going to say here is, in this equation, the force of the body is equal to mv squared over r, right? On this one, what we're going to say it's going to equal to rho instead of mass, right? So the change in pressure with respect to the normal is rho v squared over r, where r is the radius of curvature of that particular particle. So what this is saying is the change in pressure with respect to the normal direction is rho v squared over r. And I'm actually going to draw the r in here like this. So there's my radius r for this particular curve that this particle is going through. So if we take a look at this instance, we can see the pressure change in the normal direction has to be positive, right? So in other words, as we go from here to here, the pressure has to be increasing as we go outwards along the radius. So I'm going to actually rewrite this as dp dr, right? So dp dn or dp dr. So this is the pressure in the radial direction is increasing as we go away from the center of the radius of curvature. So let's take a look at how this actually applies to an airfoil. So here's my airfoil down here. And what I'm going to do in this case is I'm going to accentuate the curvature of the streamline. So let's make it nice and curved, like that. So what you can imagine here is this particle needs to be pulled downwards by the airfoil. So the force acting on the particle, right, is going to be downwards. So force particle, which means the only thing that can pull it downwards is the airfoil. So if I take a look at this piece here, what it says is that the airfoil is being pulled upwards. I'm going to call that the force of pressure. So what we can see is as we bend these streamlines, or as we curve these streamlines, there has to be some kind of acting pressure to do that. So here, the pressure to bend the streamline is actually the pressure that's pulling the airfoil up. So let's continue this thought a little bit, right? Is the idea here is that the radius of curvature r of this particular streamline is something like this, which means that as we go outwards this way, the pressure is going up, according to our equation. So as we go further away from the center of curvature, the pressure increases, which means if somewhere out here we have P infinity, as we go in towards this airfoil, the top surface of it at least, we're going to be increasing our pressure. On the other hand, if we take a look at this portion here of the airfoil, we can see that the radius of curvature has a center somewhere over here. And in this case, what it says is we're increasing our pressure as we go this way. So this location here is P infinity is greater than P local is greater than P infinity. And the reason is we're going from P infinity, or the atmospheric pressure, to a local pressure that's greater. On this one, we're going from P infinity to a local pressure that's less. So we're going to say here that pressure is less than P atmospheric, or P infinity. So what this particular instance of Bernoulli equation gives us, or this normal Bernoulli equation tells us, is that any particle going through a curve is actually usually being pulled towards the center of that curve. And the pressure in a fluid is what causes that pull towards the center of curvature. So what's cool about this equation is you can take a look at a lot of different things. So if you look at a tornado, for instance, you can see that a tornado rotates around in circles, and it tells you that the middle of the tornado is a low pressure zone, LP, and the outer part of the tornado is a high pressure zone, which is why air and other objects get sucked towards a tornado and then brought up into the air. The same thing goes for a hurricane. The center of a hurricane is very low pressure, and they often tell you how many kilopascals the pressure at the center of a hurricane is. And if you think about what storm surge is it's the center of the hurricane, the low pressure zone is actually pulling the water up and causing it to surge. So that's an example there. Another example might be if you take a look at an object like a car. So the car has to essentially push fluid away from it in certain parts and pull fluid towards it in other parts. So you could imagine kind of predicting the pressure field around an object using the normal Bernoulli equation. For this class though, what we're interested in is this idea of anytime you see a streamline that's curved, you're actually creating a lift generation capability or a pressure difference. All right, so hopefully that made some sense. We'll talk about it some more in class.